Another kind of discrete distribution is called the Poisson distribution. And so this one is time-based. And so when we are differentiating from all of these other ones, the biggest difference is that it is time-based. So very different concept than binomial and the other ones. Instead, we're thinking about how many trains are going to come to the university station in the next hour, or how many tumbleweeds might cross my front porch. Something over time or space. In your next class in 2020, you're going to be using this to predict how long it's going to take you to do something. The formula is really complex. It's kind of nasty to look at, but of course, Excel does it for you. So we're going to use the Poisson.dist. It's asking you for the mean, which is how many you are expecting. Is asking you for the chance of that occurring, and then 0 and 1 is the same as the last one, where 0 is the mass function and 1 you will get a cumulative function. Other books and in other places they will use a lambda instead of a mu, just an FYI. So we are also assuming that the probability does not change from period to period. So in the first hour, the probability is not more likely to change than in the second hour or third hour. If so, then you're going to have to do different ones for those different time periods. So if you have a heavy time, like Starbucks in the morning, it's probably going to have a different probability distribution than Starbucks at 1 o'clock or 2 o'clock. So let's look at how we actually go about doing this. In your book, there is a window example, and it is asking you about arrival times at a bank. So what are the chances of, in 15 minutes, having different arrival times who show up to the bank? And one of the reasons we know that it's Poisson, because it talks about arrivals, it talks about time. So if you see things like that, you know it's going to be a Poisson distribution. Alrighty, so here's how we're going to set this one up. So I'm going to say that there is an average of 10, that's what we're trying to understand, 10 arrivals every 15 minutes. That's essentially what they are planning on, and they want to see what are the chances that that's actually going to happen. So I have my arrivals. What are the chances of 0 arrivals in 15 minutes? I'm going to calculate that. What is the chance of 5 arrivals in 15 minutes? What is the chance of 15 arrivals in 15 minutes? And then I'm going to go all the way down to 53. We could continue. That's just a number where I stopped. This one's easy. So equals the Poisson distribution. It is asking us for the x, so what is the arrival? What is the outcome? It is asking us for the mean, in this case is 10. And then it is asking us cumulative, true or false. This is going to be the mass function, so I'm going to say 0. I also want to go to the mean, and in the middle of it, click function F4 to lock this one in place. So it will continue these down, it will continue this one down, referencing as we go, side by side, but it's going to lock and always reference this cell. So that is my chance of 0 arrivals in 15 minutes. It's very, very small. I'm going to double click. That's going to fill all of them. So I could continue as much as I want because come on, Excel does it for you. So the chances of having a lot of people show up in 15 minutes is very, very, very small. You see the E minus 17, there are 17 zeros before that 1. So 0, 0, 0, 0, 0, 17 times 175. So if we go up here, more what we were to be expecting would be right around 8 to 12. You can see those have the highest probabilities are right in here, which is not surprising because that's kind of what we are hoping for. So we're planning on 10 arrivals per 15 minutes, and we want to see what are the chances of that actually happening. Cumulative, same thing. So equals Poisson distribution, x, comma, mean, comma, in this case I'm going to say 1. It is a cumulative distribution. I am going to make sure that I have locked that reference cell. So I could click this and drag it down if I want to, or I can just double click on this little square and it fills it in all the way down for me, which I happen to like. Expected value. As always, we are going to take x times p of x, copy that all the way down. I'm going to scroll down to the bottom and I'm just going to do a sum of this whole thing. I'm going to find out what was my expected value. Oh, it's 10. Interesting. So my expected value is 10 arrivals in 15 minutes, and that's also what I put up here. So let's change this and say that we want to expect 15 arrivals now in 15 minutes. And notice how all of our probabilities just changed, including our expected value. So we are expecting 15 people to show up in 15 minutes. You can think about this as Starbucks. If that's what you're planning for, what are the chances it's actually going to happen? Some of the chances are higher that nobody is going to show up. You can have a very small chance that a lot of people are going to show up, but in general, we're kind of expecting right here in the middle. Another thing I can do with this is say, well, what is the probability that less than 10 people are going to show up? So I can take the sum of 0 through 9. That's the probability. And then I can take the sum of 10 or more. And so I can break down essentially my expected results and try to understand this in a different way.